Here is an important problem from Gauss divergence theorem. A vector A equal to x square I plus y square j plus z square k taken over the cube. Verify Gauss divergence theorem. Then the condition for x, y, z is given here. The values of x, y and z are greater than or equal to 0 but less than or equal to 1. For that, write down the Gauss divergence theorem. Gauss divergence theorem is double integral of a dot ds equal to triple integral of del dot a into dv. This is triple integral of del dot a into dx dy dz. The given problem, the value of a equal to x square I plus y square j plus z square k. Now find out the value of del dot a. Del dot a equal to I into dou by dou x plus j into dou by dou y plus k into dou by dou z dot x square I plus y square j plus z square k. Then we know that I dot I equal to I dot I 1, I dot j 0, I dot k 0. Therefore, this is dou by dou x of x square plus dou by dou y of y square plus dou by dou z of z square is equal to 2x plus 2y plus 2z 2 into x plus y plus z. Now triple integral of del dot a dx dy dz equal to 2 into triple integral of x plus y plus z into dx dy dz. This is equal to 2 into x plus y plus z. Limit varying from 0 to 1 is also 0 to 1. First we have to make our integration with respect to dz, so that we may do our operation. X into dz plus y into dz plus z into dz. This should be multiplied by dx dy. Here also limit varying from 0 to 1. If you do the integration, you can get this is equal to 0 to 1, 0 to 1. X dz is x into z plus y into z plus z square by 2. Here limit varying from 0 to 1 into dx dy. And this is equal into 2 into, apply the value of z equal to 1, we can get x plus y plus 1 by 2 is dx into dy. Limit from 0 to 1, here also 0 to 1. If you apply the upper limit for z, you may get z equal to 1, you may get x. Here is z equal to 1, y. Here is z equal to 1 by 2. If you apply the lower limit, everything is vanished. Now we have to integrate this equation with respect to dy. This is equal to 2 into double integral of x into dy plus y into dy plus 1 by 2 into dy. Entire is multiplied by dx. Limit varying from 0 to 1. This is also 0 to 1. Now we have to integrate with respect to y. It is 2 into 0 to 1. To do the integration with respect to y, x into integral of dy is y. Here x is a constant. Plus y dy is y square by 2. Plus integral of dy is y. This is y by 2. Apply the limits. Lower limit 0, upper limit 1. Entire should be multiplied by dx. This is equal to 2 into limit varying from 0 to 1 x, because y equal to 1. Apply the limit. Plus 1 by 2 plus 1 by 2. Entire is multiplied by dx. This is equal to 2 into x plus 1 into dx. Now the limit is varying from 0 to 1. If you take our integration process, integral x dx plus dx, limit varying from 0 to 1 is 2 into x dx is x square by 2. Integral of dx is x. Now apply the limit 0 and 1. This is equal to 2 into 1 by 2 plus 1. This is 2 into 3 by 2. This is equal to 3. Therefore, triple integral of del dot A dv value for the given vector A equal to x square I plus y square j plus z square k equal to 3. Now we have to expect the same for the left hand side also. The left hand side is double integral of A dot ds. Now we have to prove that this value is also equal to 3, surface integral value. For that, come to the problem. It is a cube. The vector A equal to x square I plus y square j plus z square k taken over the cube. Then the minimum value of x is 0, maximum value of x is 1. The same condition is true for all other cases. The lower value of y is 0, higher value of y is 1. Then lower value of z is 0, higher value of z is 1. So this is a cube. Now we should find out the value of double integral of A dot ds, surface integral value. Now consider the cube. You should find out the value of double integral of f dot ds, which is equal to double integral of f dot ds for the first phase O A BC. This is the first phase. In this phase, just we will apply the conditions next. Plus the second phase is F dot ds. The second phase is B C D G plus third phase G D E F. It's F dot ds plus fourth phase E F A O. This is the fourth phase E F A O. Then fifth phase, this is F dot ds. Actually these are all not F, these are all A. In our problem they have given A dot ds, so that we will change it in terms of A dot ds double integral, that is equal to A dot ds 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 1 2 3 4 5 plus A dot ds 6 phases we have to provide. The first phase is O A B C. The second phase is B C D G. The third phase is E F G D. Then the fourth phase is E F A O. E F A O. Then the fifth phase is this one E O C D. This is the fifth phase E O C D. And the sixth phase is F A B G. F A B G. This is the sixth phase. Now we should find out the n cap values for each and every phase, and then we will come to the conclusion about the value of double integral of A dot ds. See this diagram first. In this phase OABC, OABC, this is in the xy plane, therefore the value of z is equal to 0. Consider this phase. Here the value of y equal to 1. Y value is 1 maximum. In this phase the z is having its maximum value of 1. Opposite phase of this, the value of y equal to 0. There is no y value here because it is in the xz plane. Here the value of z is 0, here z is 1, here the value of y equal to 1, here the value of y equal to 0. In this plane the value of x equal to 1, whereas at the middle phase, that is the F A B G, the value of x equal to 0. Now you should apply the conditions to evaluate this. Take the first integral, double integral A dot ds O A B C. It is modified as double integral of A dot n cap ds O A B C. This is equal to double integral of OABC. What's the value of OABC here? OABC. Here the value of Z equal to 0. Z equal to 0. Then in this plane, in this phase OABC, then this is opposite to z-axis. Along the z-axis, the unit vector n cap value is k, but this is opposite to this z-axis. The n cap value is minus k. Here the n cap value is minus k. A dot minus k, then the value of ds is dx dy. This is the first integral. Now the value of a is x square I plus y square j plus z square k is dot minus k into dx dy. Here the value of z is equal to 0. Double integral of, see that I dot k 0, j dot k 0, k dot k 1. So with a negative sign, z square dx dy. Here the value of z equal to 0. Therefore automatically this integral value is 0. This is equal to 0. So the integral a dot ds o a b c equal to 0. So the first integral, this value is 0. Now take the second integral, a dot ds bc dg. Double integral of a dot ds bc dg. bc dg. See this phase bc dg. Here the value of y is 1 maximum. bc dg, y is maximum, then n cap value is j, because along the y j component is present. Here in this problem, this is modified as bc dg a dot n cap into ds, which is equal to a dot, the value of n cap is j, then ds is dx dz. Here the bc dg y value equal to 1. So automatically we should use the rest of the quantities, dx into dz. Now we have to evaluate this integral. The value of a is x square I plus y square j plus z square k dot n cap value is j into dx dz bc eg, and y equal to 1. This is equal to triple integral of, say, j dot j 1. This is y square dx dz. Here the value of y equal to 1. Therefore this is modified as dx dz. This is 0 to 1, this is 0 to 1. X lower limit is 0, upper limit is 1. Z lower limit is 0, upper limit is 1. Therefore, the integral value is 1 because the integral of dx is x. If you apply the upper limit, we can get 1. Then you may get dz. Integral of dz is z. If you apply the upper limit, 1. So the total result is 1. This is equal to, first integrate with respect to z, you may get z dx, which is equal to upper limit is 1, integral dx. If you integrate this, you can get x, limit varying from 0 to 1. So the answer is 1. Therefore, the double integral of a dot ds interface BC dg equal to 1. So this value is 1. Next, find out the value of double integral of a dot ds EFGD. Double integral of a dot ds EFGD, which is equal to double integral of a dot n cap ds EFGD. Come to the face EFGD. EFGD, here the value of z equal to 1 because z component is dominating. Z equal to 1. Put here z equal to 1. Then what is the value of n cap? See this EFGD. Along the z, the k component is present, so that the value of n cap is k. This is equal to integral, the value of a is x square I plus y square j plus z square k into n cap value is k because z equal to 1. This is integrated with respect to dx and dy. Now this is simplified as, say, k dot k1 is z square dx dy. Here is z equal to 1. Therefore this is double integral of dx dy, then limits varying from 0 to 1. So the answer is 1. If you integrate this, we can get 1. Double integral of EFGD a dot ds value is 1. Now come to the, this is 1. Now EFAO, next integral. Double integral of a dot ds EFAO, which is equal to double integral of a dot n cap into ds is equal to double integral of a dot, what is the value of n cap? EFAO. Go to the face EFAO. Here the value of y equal to 0. So this is the component opposite to this y. N cap value is minus j. Y equal to 0, then n cap is minus j. Here EFAO y equal to 0, then n cap value is minus j, y equal to 0. Therefore, we have to integrate this with respect to dx and dz. This is the value of ds equal to dx dz. Then this is equal to double integral of x square I plus y square j plus z square k dot minus j into dx dz. Here y equal to 0. J dot j 1. This is equal to, so here j dot j 1 y square dx dz. Here the condition is y equal to 0. Therefore, this integral is 0. So double integral of a dot ds EFAO equal to 0. Now go to that part. This part is 0. Next EOCD. The next integral is double integral a dot ds EOCD, which is equal to a dot n cap into ds EOCD, which is equal to double integral of a dot, go to EOCD, this is the face, EOCD, this is the face. In this face, the value of x equal to 0. See this EOCD, x equal to 0. Therefore, the unit vector n cap is minus I, opposite to this. Here x equal to EOCD, x equal to 0. Then unit vector is minus I. Then dy dz. ds is dy dz because x equal to 0. This is equal to x square I plus y square j plus z square k dot minus I dy dz. Here x equal to 0. I dot I 1. Therefore, x square dy dz. Here the condition is x equal to 0. Therefore, this integral is vanished. Then double integral of a dot ds EOCD equal to 0. Now go to that part. This is also 0. Now come to the final part. A dot ds FABG. Double integral of a dot ds FABG, which is equal to double integral of a dot n cap into ds FABG. Go to the face FABG. See, this is the face FABG. Here the value of x equal to 1. In this face, x equal to 1. Then n cap is equal to I. This is equal to double integral of FABG x equal to 1, then A dot n cap is equal to I. Then ds is dy dz. This is equal to double integral of x square I plus y square j plus z square k dot I into dy dz. Here the condition is x equal to 1. Now I dot I 1. So this is equal to double integral of x square dy dz. Here x equal to 1. This is equal to double integral of dy dz. 0 to 1, 0 to 1. If you integrate this dz, you may get dz, then limit varying from 0 to 1, which is equal to dy into 1, which is equal to integral dy. Then if you integrate this, you can get y limit varying from 0 to 1, that is equal to 1. So the integral value A dot ds fa bg is also 1. Now go to this. This is 1. Therefore, if you add these things, 6 factors, 1 plus 1 plus 1, 3. Here we have proved that the integral f dot a double integral, here also double integral, a dot ds, a dot ds equal to 3, because we are adding the 6 factors, 6 integrals. See this, a dot ds equal to these things. First integral is 0, second integral is 1, third integral is 1, fourth integral is 0, fifth integral is 0, but sixth integral is 1. If you add all these things, we can get the value of double integral of a dot ds equal to unity. A dot ds is 3. And already we have proved that triple integral of a dv equal to 3. Both the sides are equal. Hence we have verified the Gauss divergence theorem for the given problem.